Hello everyone, it's Benny, and in this video we're going to be talking about cameras. Some way we can specify the point and direction that we're looking at the world from. And that's going to be the topic of this video. So let's go ahead, dive in, and get started. Now, just to give you an example, let's say this is this is an illustration of what we're sort of going for. We have some box, and as you see, it has some distance from the camera. We're going to have to simulate that somehow. And as you also see, there's sort of like a viewing cone. So, because, you know, we have sort of perspective distortion. If I'm looking at some railroad tracks, just to use a contrived example, you know, I don't see two straight lines. They sort of like converge inwards towards the center of my view. And that's the second thing we're going to have to simulate. So there's sort of two problems to this. The first is sort of orienting all the objects so that they illustrate the offset of the camera. They illustrate, well, the position and orientation of the camera. And the second part of the problem is simulating perspective. I'm going to start with simulating perspective, because that's a lot easier than it sounds like. So to go off on my previous example, we've got some railroad tracks. And this is how we're representing them in our world. We got some lines, they're sort of going in between each other. And it's nice, but that's not at all what we see in reality. We see them sort of converging inwards and whatnot. And yeah. So how do we simulate that? How do we get it so that all of them converge in the way we see things, well, in reality? As it turns out, this is very easy. All you have to do, take the x and y positions of everything, divide it by z. It's that easy. And that ends up with something like this. Much more akin to what you'd expect to see. Everything sort of goes in towards the center. Things get, smaller as they fade off into the distance. All that stuff. And the thing about this, the reason this works, is because in OpenGL, the center of the screen is at position 0, 0. When I divide x and y by z, if x is at 500, I'm dividing it by 20,000, that gets a number that's pretty close to 0. If x is 500 is divided by 1, it's only 1 unit away, that's 20,000. So, you sort of see the idea here. As z gets further and further away, x gets sort of scaled down closer and closer to 0. And same thing for y. And really, it's that easy. There's nothing else to perspective projection. That said, there's a few more things you're generally going to want to do. For one, you're going to want to simulate field of view. So your viewing angle, if you've ever done any photography or something, you've probably done something with this, although you may or may not have called it field of view, but, just adjusting the viewing angle. And as you see, there's sort of the illustration of that. It's the angle between the, these things. I think the image explains it better than I could with words, so I'll leave it at that. But yeah, that's one thing you want to simulate. And ultimately, all that ends up amounting to is I should say scaling things in, depending on how big this angle is. Other thing you want to simulate is aspect ratio, because, well, your typical screen or window is a little bit bigger on one axis than the other, and if you just draw everything like this, it's going to assume your image is a square. So if you try projecting a square into something that's not a square, you get things sort of stretched and distorted, and it doesn't quite look like what you'd expect. Especially with rotation. Rotation just looks absolutely bizarre when you do that stuff, but I digress. And there's also one other thing. And that is the z, because you're not just dividing x and y by z, you're also dividing z by z. You're dividing everything by z. So the question ends up being, how do I preserve my z value? How do I get it so that my, z value ends up being what it was before, even after it's divided? And that ends up being a little bit trickier than you might expect. It has some interesting math. And really all this stuff is just math at the end of the day. It ultimately ends up as just being scaling things in, except actually the z thing has some translation going on, but that's another topic. That's a whole bunch of interesting algebra. So yeah, most of it's just scaling things in. The bulk of the work is just done by dividing everything by z. If you want to know how this math works, I'll direct you to a certain website I'll post in the description, which has a tutorial on perspective projection. I personally found it the most understandable explanation of perspective projection and the math behind it, so I'll leave you to that. I think that does a better job explaining it than I would in this video, so yeah. And yeah, so ultimately all these different factors that allow us to project things properly end up being in something we call the projection matrix. One thing to note though, the projection matrix does not include the division by z. The reason for this is your graphics hardware actually has a feature that lets it automatically divide everything by z. And we're going to be taking advantage of that. But yeah, so this includes the field of view, the aspect ratio, the z correction where you got to make sure the z is right even after it's divided by itself, which, interesting mathematics. Yeah. And yeah, it includes all that, but not the division by z. And that's the first part of the camera conundrum. The second part of the problem is simulating the camera's position and orientation. Because, well, I'm going to see a completely different part of the world if I'm looking to my left rather than looking forward. So, you know, I gotta have some way to simulate that. And let's look at it like this. I have some positions, you know, well, I should say points, vertices, you know. At the end of the day, everything in our scene ends up being points. We can have texture coordinates and texturing, and we can have whatever other fancy effect we want with it. But at the end of the day, we're representing everything with points. And we have our camera. As you see, our camera is offset from our points. It's not at the position of the points, it's moved, well, back, moved a bit to the left. How can we simulate that? Because at the end of the day, we got to translate everything into the sort of position space that the GPU understands. And the way we're going to simulate this is by taking everything in the world and moving it the opposite of the camera. So if I'm moving the camera to the left, I'm going to move everything in the world to the right. And that's going to sort of simulate the camera's motion. Because, well, it makes sense. If I move my head to the left or something, then you notice everything that I see in the world sort of moved to the right. I can do a sort of similar thing with rotation. If I rotate to the left, it's sort of like everything in the world being rotated to the right, except with my sort of face as a center point. So, you know, that's how we're going to simulate things. And a lot of people seem to think, whoa, wait. If we're doing this sort of moving everything in the world on every single point in the world, isn't that going to get really, really computationally expensive? And it could, but there's a little bit of a mathematical trick. Because, you see, moving things to the left, rotating things around our face or camera, whatever you want to think of it as, well, that's sort of like transforming everything in the world, you know? And transformations are good candidates for matrices. And matrices can be applied in our vertex shader, which is already being applied anyways. So yeah, that's the trick. We're going to have a view matrix to represent that. And just like with our actual objects, well, I don't know if we'll call it normal motion, but you know, object moving left and right, rotating around, our 3D motion. In addition to that, we're also going to have the view matrix to apply it. And the same way we're going to apply to the projection matrix. So, yeah, there is a cost to it, but once we assemble the matrix, because again, remember, we can just multiply matrices and get one final matrix that we apply to everything, rather than applying these matrices sort of first the motion matrix, then the view matrix, then the projection matrix, and stuff. No, we can just multiply them all together, get one final matrix, and then ultimately ends up being just as cheap as moving everything around in the world in the first place. Well, normal motion, I should say. So yeah, there's really no significant cost to it. It's using the same vertex shader trick as everything else in the world. And yeah, that's how we're going to represent cameras. So let's go ahead, dive into the code, and get started. Okay, so let's go ahead and get started. I went ahead and created the camera header file, and I included GLM and the transform classes of GLM, because you probably figured this out already, but we're going to need some transformation stuff to do all the matrix math for the camera. So yeah, And this is going to be kind of like transform. It's going to be just basic header only, not going to do too much with this class. Mostly just an example to show you how cameras work. So, anyways, I'm going to create a constructor. This one's going to take, I'm going to take in a GLM vec3 reference called pos. So the position of the camera's in. I'm going to take in some float, f of v, field of view, and some float aspect for the perspective projection. I'm also going to take in two more things, a float z near and float z far. What z near and z far are they're sort of like the minimum distance, the closest distance we can see, that's z near, and the furthest distance we can see, that's z far. And this prevents us from seeing things that are either infinitely far away, or from having some weird issues where we see something that's like directly at our eye point and it can't decide if we should see it or we can't see it, you know. It prevents weird things like that from happening. So, yeah, that's what those are for. Now for private, here's the sort of variables I'm going to have. My first variable is going to be a GLM mat4, matrix 4. I'm going to call it perspective. So this is going to be the perspective matrix. And my perspective is going to equal GLM perspective. And it takes in a field of view, an aspect, a z near, and a z far. So we can just pass those parameters in and leave it like that. I'm not going to be calculating this sort of with a function like I am in the transform class with getModel, because perspective matrix really isn't going to change unless the window's resized. You might want to have something where the camera gets updated when the window gets resized. That's, whoops, an idea for a future improvement of this, but I'm going to do it like this, just for example, just to show you how things work. Next thing, I'm going to have another variable in camera, or another member variable. I'm going to call m_position, the position the camera's in. And you're never going to guess this, but I'm going to initialize m_position to the position we pass in. Now rotation. There's a lot of ways you can represent rotation in 3D. I'm going to choose a certain way of doing it, and this may or may not be ideal for you, but I'm going to do it like this, just to sort of show you how this way works. And because it genuinely is a good way of representing rotation for cameras. It's with two vectors. One vector, called mForward, which represents the forward, whatever direction is forward from the way you're looking. And the other is m_up, which is whatever direction you perceive is up. So, for example, if I can look any direction I want with my head or something, but I always have sort of like the same idea of what direction is up for me. So that's sort of the purpose of this. Well, there's always some direction that's up, you know. And yeah, so that's sort of the idea behind these. I'm not actually going to take in parameters for these. You might want to do that, but I'm not. I'm just going to hard-code them. Forward is going to be a vector, GLM vec3 of 0, 0, 1. So forward is going to be straight down the z-axis, looking straight into the screen. And up, m_up, is going to be 0, 1, 0. 1 on the y-axis, looking, so up's going to be, well, the y-axis. And yeah, you can play around with this. For example, if you've played with some other 3D programs, and some of them say, hey, you know what, y isn't up, z is up. This is a pretty easy way to do that. Just set forward to the y-axis and up to be the z-axis, or something like that. And you can do that. And the idea is you would rotate by, well, rotating the vector, the forward vector, and the up vector by some amount. And that's the idea of how you do rotation with this. I'm not actually going to do that, I'm just going to leave them hard-coded, but you might want to have getters or something for these in the future, especially for like forward, up, and position, so you can change them. Again, I'm not really that focused on that, though. I'm more focused on just showing you how you can set up a camera. And with that, we have our camera initialized. So it's time for our function, our equivalent of the getModel. Except in this case, it's going to be inline GLM mat4, called getViewProjection. The reason for this is it's the view times the projection. And it's const. Just like with another thing. In transform, they get model. And actually implementing this is going to be very, very easy because GLM provides a nice convenient function that makes it really easy to do camera rotations called GLM look at. You start at some position and it's saying what position you want to look at, and actually I believe it's capital A look at. So you look at starting off with the camera's position, which would be called m_position. And the next parameter is what position you want to be looking at. And the position I want to be looking at is going to be my position just plus m_forward. So that should just move 1 unit along forward, and so that should give me a valid position to look at. And finally, it takes in whatever direction is up, so I'm going to pass in m up. And it's almost that easy. The only thing I have to do now is take in perspective, multiply it by that to apply the perspective projection, and there you go. We have a view projection. And honestly, that's all you have to do to get a camera set up. Again, you might want to have getters or something, or some convenience functions for rotating with the forward vector and up vector and whatnot. But this is all you need to do to get a basic functioning camera with perspective enabled. So in my main class, my main file, main.cpp, I've already included camera.h, so I'm going to create a camera here. I'm going to call it camera. I'm going to take in, I don't know, GLM vec3. Let's move -3 units back on z. Field of view, I'll say GLM. Actually, does GLM have a function for that? I don't believe it does, now that I think about it. Okay. Does GLM have some sort of radian conversion function? Well, no, I'm going to look at that. And I'm an nincompoop because I forgot that it just takes it in degrees, so I don't need to convert it to radians. So yeah, I'm going to set an field of view of 70 because that's approximately what the human eye sees. Not exactly, but it's approximately. It's actually very difficult to model exactly the field of view of the human eye. But that's a decent approximation. For my aspect ratio, I'm going to say display. I don't have functions for that. You know what? I'm not even going to bother. I'm just going to have some macros here. I'm going to define width as 800 and define height as 600. I'm going to pass that into display. Again, a better way would probably be to go into the display class and have a get width and get height function, but since this is just a basic example of how things are done, I'm not going to bother with that. I'm going to make sure you convert this to floating point division, because otherwise this will probably just be 1 or 0 in most cases. That's not going to work, so yeah. Do float width, and because I'm paranoid, I'm going to cast it to float height. You shouldn't need it, but I'm paranoid. And there. And that should give us the aspect ratio. For Z near and Z far, I want... Again, the Z near thing is mostly just to prevent the case of something's exactly at the eye point and you have some sort of weird, it can't decide if you're seeing it or if it's behind you, so I'm going to set that to 0.01, just something very close to the eye. And for Z far, that's mostly so we don't see out into infinity. So I'm going to set this to 1000.0f. Now you don't want to set these too far apart, or you can actually run into some floating point precision errors. But these I find are generally some pretty good values for it. And that should give us a camera we should be able to build and not crash, or, it should actually build. Of course, we're not using the camera, but we should have it. Now, to use the camera, I'm going to take that in the shader update, because, we have to apply all this in the vertex shader. So, in shader.h, I'm going to pass in a const camera reference camera. And it's going to, of course, need to include camera.h. And in shader.cpp, I honestly can... You might want to rename your variables in your shader to MVP rather than just model to more accurately represent what's actually happening right now, but right now what we can do is we can just say camera.getViewProjection times transform.getModel. And it should be that simple. Oh, and you need to pass in the camera. And there, so now we should see our triangle. Yeah, look at that, in perspective. And in fairness, scaling does look in fact, yeah, let's get rid of scaling for now, actually. Because it's not helping us appreciate the perspective that's going on. Yeah, look at that! We've got it in perspective. So you see, it doesn't have that weird rotational distortion it had before because of the, aspect ratio discrepancy. And I can move the camera closer, like, say, -1 unit away. And, hey, look at that! We're a lot closer to it. And I can even say something like transform.getPosition.getY is cosine counter. And probably want to actually set this 2 units away. So now it should be moving sort of closer and further away from the... Oh, right, that's Y, not Z. Whoops. Position.Z. There. So yeah, now it's sort of getting closer and further away from the camera. So yeah, we're getting, I think, a pretty nice sense of perspective of all of this. And, you know what? Sure, let's have some more rotation. Let's set rotation, yeah, all axes to this. Just do absolute, bizarre, wacky rotation of nonsense. There, look at that. I don't know about you, but this looks pretty 3D to me. Got a big, rotating triangle in 3D space that's spinning around, getting closer and further away in perspective. Yeah. So there, we've got a triangle. And we can stop here if we want. But there's one more sort of bonus thing I want to cover in this video. Actually, you know what? I'm happy. I think we should keep the video focused on just the camera. So thank you. Hope you enjoyed, hope you learned, and in the next video, we're going to pretty much wrap up the series. We're going to go over a little bit of bonus content, a little bit of extra stuff for the series, and then we're just going to wrap things up, because this is most of what I wanted to cover. So thank you, hope you enjoyed, hope you learned, and see you next time.